Good evening. This is the first time we use this online teaching method, and I would like to start on doing the classwork that I posted online already over 10 days ago, and we would like to go over them as conversion test part. The first we're going to encounter is this example of the sum of 1 over 2n plus 3. And we notice that 2n plus 3 is less than 2n plus 4. And therefore, and this is true for all n positive integers, of course. So the sum from, let's say, 1 to capital N of 1 over 2n plus 3 is going to be bigger than 1 over 2n plus 4 for the same range of 1 to n. Now, in order to allow us to make an easy transition to compare with a known converging or diverging series, we want to do a factorization, let's say from half, and this is going to be n plus 2, as you can see also from 1 to n. And now by suppressing the denominator down to n, hence increasing the lower and upper limit by 2, so the summation is now from 3 to n plus 2. And this allows us to see a comparison with just the usual summation of 1 over n from 1 to capital N. And we know that the series is going to diverge to infinity as n goes to infinity, thus proving the original series is diverging. So by comparison test with this known series of 1 over n. There may be other ways of getting the same estimate, but this is one way to do it. For the second example, again, we do a quick analysis of the numerator and denominator. So n plus 4 to the power n over n plus 6 to the power n. Now this is obviously going to be bigger, to be less than twice of the 4 to the power n when n is large, some n. And at the same time, the denominator can also be overestimated by deleting the n. So this is what we end up with for some n bigger than some capital N. Okay, let's perhaps call this, instead of, I call this n0, okay, for some n0. All right, and then we see that this is going to be equal to twice of the 4 to the power n over 6 to the power n. Okay, so that's for when n is bigger than n0. So now we do a summation. Okay, and the summation starts from n0 to some capital N, and so this is from n0 to capital N, so that when this holds, we make sure that this inequality here holds. Okay, so here is also from n0 to capital N. All right, so now we can continue the comparison. So the I get a factor the 2 as a common factor from n0 to capital N, and then we notice we can simplify the 4 over 6 into 2/3 to the power n over 3. So we see that this actually converges because it is a geometric series as n goes to infinity. I should put capital N by comparison. Hence, the original series 1 to infinity converges by the comparison principle with the sum of 1 to infinity of 2/3 to the power n. So that would solve the problem. The next example is to try to consider whether this is going to converge, and if it converges, you use the first 10 terms to approximate the converging series and see how big the error term is. Okay, so to determine whether this is converging, we could, it's actually quite easy to see, because just like what we did earlier, we look at the individual term, and the numerator is bounded between 0 and 1, where the denominator is like k to the power 3. So that tells us it would converge by comparison test. So the sum converges by comparing with sum over 1 over k to the power 3, which is known to be convergent, and you can apply integral test if you need, if it is needed. Okay, so the error term of estimating 10 terms can be done with the following. In fact, the error term of n terms is given by the integral from n to infinity of okay, let's slightly recall that the integral itself from n to infinity of sine square x divided by x to the power 3, because this is less than from n to infinity of dx over x to the power 3, and this you can compute. This turned out to be 1 over 2n to the n squared. So this is the error term, and so therefore the error term is going to be between these two, namely that the integral of the function, that is the sine square x over x to the power 3 dx from n plus 1 to infinity, and this is equal to s minus sn, and this is less than the integral from n to infinity, which we just computed, and this we know is going to be less than 1 over n squared if you just consider n terms. And now you require 10 terms. So you want to see how the error term is. So in this case, you're going to put in 10 for 1 over n squared, so you're going to have twice of 10 squared, which is equal to 1 over 200, right? And that's equal to 0.005. Okay, so the error term is going to be less than this if you use 10 terms. So that solves this problem. Then the next one on the next page is, excuse me,